Okay. So in 3.3, we're talking about the addition rule. As 3.2, we're talking about the multiplication rule. So in 3.3, we're talking about an event happening, and it can happen in multiple ways. What's probably that it happens this way, or this way, or that way? So when we're talking about that, we're talking about mutually exclusive versus overlapping events. All right, in section 3.2, you learn how to find the probability of two events A and B occurring in sequence. Such probabilities are denoted by probability of A and B. In this section, you will learn how to find the probability that at least one of two events will occur. Probabilities such as these are denoted by probability of A or B. Okay, so that's a huge difference. That's very small in their wording, but very big in the way that you can do the problem. So again, the probability that the probability that A and B both happen, so two events occurring in sequence, versus the probability that one thing is going to happen, and it's going to be either A or B. So not two things happening, but one thing happening that could happen two or more different ways. All right, mutually exclusive. What's the definition of mutually exclusive? Two events A and B are mutually exclusive when A and B cannot occur at the same time. So if we're talking about the probability that an event happens and it's either going to be A or B, it's mutually exclusive when they can't happen at the same time. When it can't be both, it's called mutually exclusive. It has to be either one or the other. So it's like you either pass or you fail. All right, it can't be both at the same time. All right, the light is either on or it's off. Can't be both at the same time. All right, this Venn diagram shows a relationship between events that are mutually exclusive and events that are not mutually exclusive. Note that when events A and B are mutually exclusive, they have no outcomes in common. So the probability of A and B both being the case is 0. It can't be both. Like, look at this Venn diagram. A and B. There's no overlap there. There's no way it can be in both circles at the same time. It has to be either in the A circle or the B circle. It can't be both. They're mutually exclusive. In this Venn diagram, there is a possibility of being in both circles at the same time when you're in this part that overlaps. So they're not mutually exclusive. In fact, we call that overlapping. Determine whether the events are mutually exclusive. Explain your reasoning. Okay, rolling a 3 or rolling a 4. Are they mutually exclusive? Yes, they are mutually exclusive. You can't roll a die and it land on a 3 and land on a 4 at the same time. It will either land on a 3 or a 4, but it can't do both. So it's mutually exclusive. The second one, select a male student or select a nursing major. The question is, can it be both? Can you select a student who is both a male and a nursing major at the same time? And the answer is yes. There are students who are male who are nursing majors. So in number 2, they are not mutually exclusive. They are overlapping. All right, number 3, randomly select a blood donor with type O blood. Randomly select a female blood donor. Again, what the question is, can you be both? Can you be both type O and female? Yes, there are females with type O blood. So this is not mutually exclusive. It is overlapping. Let's do these try it yourself ones real quick. Try them yourself and then we'll go together. You can pause it. All right, here we go. Select a jack or a face card. Can you do both? Yes, because a jack is a face card. What about select a jack from the deck and a heart from the deck, or a heart? Can you be a jack and a heart at the same time? Yes, there is a card that is a jack of hearts. So those two things I just said are both overlapping. They're not mutually exclusive. What about getting a vehicle that's a Ford or a Toyota? Those are mutually exclusive. There are no vehicles that are both Fords and Toyotas that I know of. Maybe there are, but I don't think so. It's either a Ford or a Toyota, not both. All right, so the addition rule. The probability that events A or B will occur, so one thing is going to happen, it's going to either be A or B, is given by probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. If the events are mutually exclusive, then the rule is simplified to simply probability of A or B is simply probability of A plus probability of B. Why? Because if they are mutually exclusive, then the probability of A and B both occurring at the same time is 0. So you would just be subtracting 0. All right? In words, to find the probability that one event or the other will occur, you add the individual probabilities of each event and subtract the probability that they both occur. As shown in the Venn diagram at the left, subtracting probability of A and B avoids double counting the probability of outcomes that occur in both A and B. All right, so if you're talking about two events occurring and it's an and statement, like what's the probability that event A and event B both occur, like getting a king and then getting a queen? When it's an and thing in probability, you multiply. When it's an or, when it's an or statement, like what's the probability of getting a king or a queen, then you add. And means multiply in probability, or means add in probability. All right, now what's this stuff about subtracting the probability of A and B? I'll tell you about that in just a second. I'm going to do a very simplified example. If I had you guys in class, I would be able to do this a true example by counting those of you who would raise your hand according to these questions. I would say something like, raise your hand if you play a musical instrument, or have ever played, or if you play a musical instrument. And let's say we had 5 students raise their hand. Let's say we have 20 students in the class. Okay, 5 students play an instrument, and I'd say raise your hand if you played on a sports team for your high school. If you played on a team in a sport for your high school, and let's say 7 students raised their hand for that. What's the problem? The problem is there could very well be students who raise their hand to both of these questions. Maybe 2 students raise their hand to both of those questions. So 2 were both. Because it's not mutually exclusive. You could play an instrument and play a sport. So we'd say the probability that a student played an instrument or played a sport is equal to what? We say the probability of playing an instrument is 5 out of 20, plus the probability of playing a sport is 7 out of 20. But we counted these two both times. They got counted twice. So that's going to throw us off. How do we account for that? We subtract them one time. Since they got counted twice, if we subtract them once, then that means they'll only get counted once. So the total answer to that question that I'm making up in this case would be 12, it would be minus 2, would be 10 out of 20, which would reduce to 1/2 or 50%. Okay. Here are the examples from the book. You select a card from a standard deck of 52 playing cards. Find the probability that the card is a 4 or an ace. All right, a 4 or an ace. All right, what we could do there is we could say, what's the probability that it's a 4? Well, there's 4 4s in the deck, so 4 out of 52. What's the probability that it's an ace? Again, there's 4 aces in the deck, so 4 out of 52. Are there any cards that are both 4s and aces? No. It's mutually exclusive. You either are a 4 or an ace. You can't be both. So that makes it simple. We don't have to subtract anything. That gives us an answer of 8 out of 52, or 2 out of 13, I believe is what that reduces to. Okay, so those would be considered mutually exclusive. All right, number 2, you roll a die. Find the probability of rolling a number less than 3 or rolling an odd number. What's the probability of rolling a number less than 3? Well, that would be 1 and a 2, right? A 1 and a 2, so that's 2 out of 6. Plus, what's the probability of rolling an odd number? Well, that's 1, 3, or 5, so that's 3 out of 6. Right? But the problem is we counted this one got counted in both categories. 1 got counted twice. So we need to subtract the probability. We need to subtract the probability that you are both less than 3 and odd, which is just 1. 1 is the only number that is less than 3 and odd, so it's 1. There's only one example there, so 1 out of 6. So now we add that and subtract. That's going to be 5. That's 4 out of 6, or 2 out of 3, or 0.667. I want to do this one on the try it yourself. Go ahead and do that one, and then we'll do it together. Okay, a card is selected from a standard deck of 52. Find the probability that the card is a face card or a heart. All right, a face card. All right, looking back at our picture here so you can get a good feel for it. The face cards are, let's see if I can highlight them, are all of these. Let me get are all of these. Oh, that didn't work good at all. That's not a highlighter, that's like a crayon. Oh, is there a highlighter somewhere in this? I can't figure out how to do a highlighter in this program. So the face cards are all of these. Oh, that's hard to write. Are all of those. Those are the face cards. The face cards are the Jack, Queen, King, and Ace. I think. Or maybe it's just Jack, Queen, King. I think I'm wrong with the first thing I said. I think it's just Jack, Queen, King. Maybe. I'm not sure. Let's just say it's just the Jack, Queens, and Kings because those are the face cards. Let's just say it's those, okay? It may include the Ace, I'm not real sure. But the Jack, Queen, King, the probability that you are a face card, if we make that assumption that it's just the Jack, Queens, and Kings, would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 out of 52 for the face cards. Now, what's the probability that you're a heart? Well, the hearts are all of these. So how many of those is it? 13 out of 52. But again, the problem is that we have counted some of these cards in both categories. We counted, let me get a good color here. We counted these cards twice. So how many cards did we count twice? We counted 3 of them twice. So minus 3 out of 52. Okay. And the total answer to that question would be, let's see, 25 minus 3. I believe that's going to be 22 out of 52, or 11 out of 26, if we reduce it. Example 3 here. The frequency distribution shows volumes of sales in dollars and the number of months in which a sales representative reached each sales level during the past 3 years. Using this sales pattern, find the probability that the sales representative will sell between 75,000 and 124,999 next month. All right, so between 75 and 124,999, well, that would be between 75 and 124. That would be this one and this one, right? So it's just going to be 7 out of, what's this total? So I think the total is 36 if I added it correctly. So 7 out of 36 plus 9 out of 36. Did we count anything twice? Like, is it overlapping or is it mutually exclusive? You're either going to be here or you're going to be here. You can't be both. So we don't have to subtract anything. So that's just going to be 16 out of 36. Or if we reduce that, I believe it would be 4 out of 9. Example 4. A blood bank catalogs the types of blood, including positive or negative Rh factor, given by donors during the last 5 days. The number of donors who gave each blood type is shown on the table. A donor selected at random. Find the probability that the donor has type O or type A blood. All right, type O would be here. That's the total of type O. The type A would be here. Total of type A. The total of everything is 409, so it's just 184 over 409 plus 164 over 409. And we don't have to subtract anything because you can't be both. There's nobody that's going to be both O and A. They're 2 separate categories. They're mutually exclusive, not overlapping. So we don't have to subtract anything. We add that together and we get, let's see what we get. We get 348 over 409. All right, number 2, find the probability that the donor has type B blood or is Rh negative. So here's the Rh factor right here, Rh negative. Probability that the donor has type B or is Rh negative. So type B would be 45. So 45 out of 409. Rh negative is going to be here, the total of that, right? Adding up all the negatives would be 65. So plus 65 out of 409. But they're not mutually exclusive. They're overlapping. You can be both. So we counted this 8 got counted when we added down that column, and it got counted when we added across that row. So the 8 got counted twice, so we got to subtract that overlap right there. So we're subtracting 8 out of 409. to get a total. It has 102. 102 out of 409 is my total answer. Here is a good summary of everything that's been learned so far in our probability basics. So if you want to read through that table, that'd be a good idea. All right, example 5. We have this graphic here telling us about the draft, a different breakdown of the 2012 NFL draft. Okay, use the figure to find the probability that a randomly selected draft pick is not a running back or a wide receiver. In this graphic, I'm noticing that there are 253 players total. I'm noticing that here are the wide receivers, here are the running backs. So I could add up all the other positions. And by the way, no players would be both here. I could add up all the other positions, or I could do the complement, which is a little bit easier. It's a little bit less work. I could say 1 minus. What I could do is I could do 1 minus 33 out of 253. That's the probability of being a wide receiver plus running backs. So that's 21 out of 253. So this right here is the probability of being either a running back or a wide receiver. So if I do 1 minus that result, then that'll give me the probability of not being a running back or receiver. So I need to add that together first and then subtract that from 1, or either distribute my negative and subtract both of them from 1. So my total answer there will be 50. Let's see here. Will be 199 out of 253, or 0.787. And that finishes us up for section 3.3. Good luck on that homework. I'll see you again in 3.4.